Okay, so welcome back to this next video in which we are discussing group actions. Okay, so in the previous video what we discussed was the definition of a group action by a group capital G on a set capital A, and we saw that intuitively what a group action actually is a composition table involving all of the elements of the group capital G with all of the elements of the set capital A, where the answer to what any element of the group composed with any element of the set capital A is another element in that set capital A. Okay, so that's the intuitive way that we've seen we can interpret a group action. Okay, now in order to actually be considered a group action, this composition table needs to obey two important properties. Now the first of those important properties is that whatever little g1 and little g2 that you pick from the group capital G, and whatever little a you pick from the set capital A, it needs to be the case that if you take g1 acting on the answer to g2 acting on little a, that answer overall needs to be the same as if you firstly compose G1 and G2 together in the group composition table, and then take the answer to G1 composed with G2 and act that on the element little a. Okay, and as I say, that needs to be true no matter what little G1, little G2 and little a that you pick. Okay, so that's property number one that a group action composition table needs to obey, and that's the difficult to understand one. Okay, if you were just to make up your group action composition table, if you were just to fill out all of the entries randomly, it would be very, very unlikely that it would obey this property. Okay, this is the difficult one to actually get. Okay, the other second property that a group action composition table needs to obey is slightly easier to understand, and this one concerns the identity element of our group capital G. And it basically says that the identity element of the group capital G must act on any element of the set capital A to return that same element of the set capital A back again. So it says that the identity acting on this element little a must give us little a back again, no matter what little a actually is. So let little a be any element of the set, this needs to apply basically. And intuitively, in terms of the group action composition table, what that actually means is that if we look at the row corresponding to the identity element of the group, all of the answers here must just be the headings for the columns, basically, just translated down. So any element of the set, when it's acted upon by the identity in our group, it's just going to give itself back again. So all of the entries in here are just going to be the same as the titles of the column that they're in, basically. Okay, right, so that then is the definition of a group action by the group capital G on the set capital A. Okay, what we now want to look into is how does this actually do what we set out to do? Because remember, what we were trying to do is formalize this concept that you can associate with the elements of a group, set permutations of some set. So what we really were trying to do is we were trying to formalize the notion that we can associate elements of our group capital G with set permutations of our set capital A. So how does this notion of a group action composition table actually achieve that? Okay, well, I claim that if you build a group action, if you build a composition table in the way that I've described that obeys these two properties, that indeed what you can now do is use this group action to associate each of the elements of the group with a set permutation from the set capital A. Okay, so that's what we're going to investigate now. Okay, so what I claim then is that you give me any element of the group capital G, okay, for which we've built this group action by G on the set A. Okay, so let me take an arbitrary little g as an element of this group capital G. I claim that the group action associates with this element of the group capital G a set permutation, basically, and I'm going to call this set permutation sigma and then I'm going to subscript it little g. So this is common notation for the set permutation that the group action is going to associate with this element little g. Again, this is going to be a set permutation of our set capital A. Okay, so it's going to be a mapping from the set A back to the set A. Okay, this is going to be a bijective map, and therefore is going to be a set permutation. Okay, so how am I actually going to define this mapping then? And you might like to have a guess as to how we're going to do this. Okay, so here comes the answer then. So the way I'm going to define this is that the mapping sigma g, the mapping that I'm going to associate with the element little g, is going to map any element of our set capital A onto what the element little g acting on that element little a is equal to. Okay, so it will send any element of the set onto g dot that element of the set. Okay, and that's how I'm going to define the set permutation that is associated with any element of the group by this group action, basically. Okay, so intuitively, in terms of our group action composition table, what this actually means is if you want to know what set permutation we're going to associate with any element of the group, little g, go to the group action composition table, find the row that is associated with that element little g. Okay, so here's our little g, here is the row that's associated with that element little g. Okay, and quite simply, it's going to send any element of the set capital A onto g dot that element, basically. Okay, so all the elements of the set are going to be mapped onto the entry that's below them, i.e. in the same column as them, but in this row corresponding to little g. So if I, for instance, take some arbitrary element of my set capital A here, some arbitrary little a here, then little a is going to be mapped onto the answer here, which will be g dot a, basically, which is another element in my set capital A. Okay, so that's the way that I'm going to, from my group action, get set permutations of the set capital A, which I can associate with every single element of the group, basically. Okay, so what I now need to prove to you then is that these mappings here actually are set permutations of the set A. Okay, because at the moment I've just stated that this is the set permutation that I'm going to associate with the element little g from our group, but I haven't actually proven that that is going to be a set permutation. Okay, so firstly, what we can see is that indeed, if I define sigma little g like this, then it will be a mapping from the set A to itself. Okay, it is going to take every element of the set capital A here, and it's going to map it onto another element in the set capital A, because whatever the entries in this row corresponding to little g are, we know that they will be entries from the set capital A, basically. So indeed it is going to map all elements of the set capital A onto other elements in the set capital A. So all I need to do now is prove that this is a bijective map, basically. So I need to prove that it's injective, and I need to prove that it's surjective. Okay, now there's a nice easy way to prove that a map is injective and surjective, and that's to prove that it has a two-sided inverse. Okay, so let me just go over this, because I won't assume that your set theory is still vividly in your mind. So I'll go over why having a two-sided inverse actually shows that the map is bijective. Okay, so it's a common way to show that a map is a bijection, to show that it has a two-sided inverse. Okay, so another map which you can compose with it in either order, which will give you the identity map back again, is basically what a two-sided inverse is. Okay, so we'll show this later on, but I'm just going to state it right now. The inverse map for sigma little g is going to end up being sigma little g inverse. As I say, we will prove that later on. Okay, but for now, I just want to show you why having a two-sided inverse will prove that this map is indeed bijective. So let's just assume that we know that this is actually going to be the inverse of this, okay? It's just really so that I've got a name for the potential inverse of this, and later we will actually show that sigma G inverse is in fact the two-sided inverse of sigma G. So this just means the mapping that you would associate with the element G inverse. So G is an element of the group, so it has an inverse within the group, which we'll call G inverse, and then of course you can associate with any element of the group a set, a mapping from the set A to itself according to this, and that's exactly what we've done here. So sigma G inverse. And as I say, we will show that that is in fact the two-sided inverse of sigma G, but for now what I just want to make you understand is why showing that a mapping has a two-sided inverse actually proves that it is a bijection. Okay, so we'll just assume we know that sigma G inverse is in fact the inverse map of sigma G. Okay, right, so what I want to show then is that sigma G inverse of sigma G of A is equal to little a for all little a is an element of capital A. So let's think what this means. This means do the mapping sigma little g on all the elements of the set capital A, and then take the answer to that and do sigma G inverse on it, and then it returns it back to little a. So basically what that says is that if you first do sigma G and then do sigma G inverse, it results in the identity map, basically. It maps all elements of the set capital A onto themselves. Okay, so that's a one-sided inverse at the moment. What I also then want to show is that if I do it the other way around, if I do sigma G of sigma G inverse of little a, that again it's equal to little a for all little a is an element of capital A. And I claim that if I can show those two things, and this is exactly what it means to have a two-sided inverse, okay, so if these two things were true, we'd say that sigma G inverse was the two-sided inverse of sigma G. I want to just explain to you why it is that if you can show these two things, then you have proven that sigma G is in fact a bijective map. Okay, so the existence of a two-sided inverse proves that sigma G is a bijective map, and I want to explain to you why. Okay, so what we're going to see is that this top one here proves that the map is injective, and this bottom one here proves that the map is surjective, and of course if we have both of those, then the map is bijective. That's the very definition of a bijective map. Okay, so let's start off with the top one, and let's explore why this being true proves that sigma of G must have been an injective map, i.e. a one-to-one map. So let's think about what this means then. So we're doing two mappings in all, so I'll draw a picture for this then. So we'll need the set capital A drawn 3 times because we've got two maps. Okay, so here is the set capital A drawn 3 times. So this is A again, and this is A once more, and once again I'll colour in A in red. Okay, and the mapping sigma of G, whatever it is mapping elements of A onto elements of A. Okay, and again sigma G inverse is also mapping elements of A onto elements in A. Okay, so this firstly means do the mapping sigma G on all of the elements of the set A. Okay, so we'll firstly have our mapping sigma G here, okay, and then what we'll do is the mapping sigma G inverse here. So I'll put the second mapping sigma G inverse here. Okay, and basically the composite of these two mappings, if you compose the two of them together, the net result is that we have the identity map here, i.e. that whatever element of this set here you take, it ends up being mapped onto the same thing over here. Now I want to show you that that means that this must be injective. Okay, and the way that I can do this is quite simply do it by a proof by contradiction. Let's assume that this mapping is not injective. Okay, now what does it mean if that mapping is not injective? Then that means that at least at one point there are two elements in this set A which are distinct elements. Okay, so these are two distinct elements here in this initial domain here. that are being mapped onto the same thing in this set here in the codomain. Okay, so if sigma of g was not injective, it would be the case that at least at one point, two distinct elements or more are being mapped onto the same element here, basically. Okay, so if it was not injective, that would be the case. Now, I want to prove that that contradicts the composite of these two mappings becoming the identity mapping. And quite simply, it's easy to do this now. Sigma g inverse will now map this element in purple here onto some element in the set capital A. Okay? Now, why is that a contradiction? Well, this composite map here must then map both of these two here onto this single element over here. Okay, so that means that this map cannot be injective, and therefore it can't be the identity map, because the identity map just maps everything onto itself, so it has to be an injective map. It has to be one-to-one. But here I've shown you the composite of these two. We are sending both of these onto this element here. Okay, i.e. it will be a non-injective map. So if sigma g was non-injective, then it would not be possible that these two could compose together to give the identity map, basically. Okay. However, this top line does not actually prove that sigma of g has to be surjective, and you might like to think through why this does not prove that it has to be surjective. It does prove that sigma g has to be injective, but it doesn't prove that it has to be surjective. Okay, now of course if we're dealing with a finite set, if A here is finite, then the instant sigma g is injective, it also has to be surjective. It can't possibly not be. But if you're working with infinite sets, then you can have injective maps which are not surjective maps. Okay, you can have injective maps from a set to itself that are not surjective. Okay, and that's why this statement being true doesn't actually always hold true in the case of infinite sets, and you can think through why that doesn't prove that it's surjective. This second one is what is going to prove that it is surjective. Okay, so we're now going to do it the other way around. So I'll once again draw out the same picture. So I'll have my three sets A here. Okay, so this is A, this is A, and this is A, and once again I'll colour them all in red again. Okay, and this time I'm going to do it the other way around. So I'm firstly going to do sigma g inverse, and then I'm going to do sigma g second. Okay, so firstly we're going to have the mapping sigma g inverse here. Okay, then what we're going to do is have the mapping sigma g. Okay, and I claim once again that if I compose these two together, and that it's the identity map. Okay, so this is now the identity map. It's going to send all elements of A here onto themselves. That proves that this second mapping, sigma g here, has to be surjective, and therefore if we've proven both of these, that then proves that sigma g has to be bijective. Okay, so how can I do that? Well, once again, we'll assume that it is not surjective, and then we'll arrive at a contradiction. So let's assume that sigma g is not surjective then. Okay, now that means that there is a portion of this set, capital A here, that does not have anything in this set here being mapped onto it. Okay, so that's the meaning of not surjective, not onto, basically. There are elements in our codomain here that have no element in the domain being mapped onto them. So let's say this portion in green had no element in the domain here being mapped onto it by this mapping sigma g. Okay, so we're assuming the exact opposite of what we want to prove. We're assuming that it is not surjective. Okay, now, I claim that that is a blatant contradiction, and it's going to contradict that this is the identity map, basically. Because the identity map, which maps every element of the set A onto itself, is certainly a surjective map. Every element in here will have the equivalent element back here, which was being mapped onto it by this composite map here. Okay, and I claim that if sigma g is not surjective, then it contradicts this one being surjective. Okay, and the reason is that this is the composite of these two, or at least it's supposed to be the composite of these two, but I'm saying that if I start here, we will go on to elements in here, and no element in here will be mapped onto this green portion here. So how possibly can the composite be surjective then if this map is not surjective? Because all the answers that you'll get from the composite, the maximum number of answers you can get are all the answers that you can get from sigma of g, okay? Because sigma of g maps every single element in this middle set A here onto elements in A, and if it doesn't map anything onto this green portion, then how can the composite of these two ever map anything onto the green portion? Because this is only going to map things into here, and this mapping then is only going to map things into here. So the composite therefore is only going to end up mapping things into this portion as well. So basically, if this second map, sigma g, is not surjective, then it contradicts the composite of those two maps being surjective, and therefore it contradicts the composite being the identity map, which is a bijective map, and therefore is surjective. So, we must therefore assume that if we can compose these two together and get the identity map, that this second portion must be surjective. Okay, and that's how this, being true, proves that sigma of g is surjective. So if you can prove these two statements, if you can find a sigma g inverse for which these two statements are true, if you can find a two-sided inverse map for sigma g, then you can prove sigma g is indeed a bijective map. It can't possibly not be once those two things are true. And that's the approach that we are going to take to prove that this mapping that we've associated with this element little g from our group is in fact a bijective map. Okay, so now all we actually do need to do is prove that this mapping, sigma g inverse, does obey these two things, and then we've proven that sigma of g is a set permutation, basically a bijective map from the set A onto itself. Okay, right, so let's start with number 1 here. Okay, so we're now considering sigma g inverse of sigma g of A. Okay, and we want to show that this is just equal to A for all little a that you put into here from the set capital A. Okay, so let's just use the definition. What is sigma g of A, basically? Well, here is the definition. That is just equal to g acting on the element A. So we can turn this into sigma g inverse of g dot A. And that makes sense because g dot A, of course, is another element of the set A, and of course we can then have this function sigma g inverse acting on that. Okay, so now what we'll do is we'll just use the definition for this mapping sigma g inverse, and again we go back up here. So the mapping associated with g inverse just means take g inverse and dot it with whatever you're asking what the function is going to map, well, whatever you're acting the function on. Okay, so we're going to take g inverse and we're going to then act it on this answer g dot a. Okay, so that's what this means. So sigma g inverse of sigma g of any element little a within our set means g inverse dot g dot a. But now what can we do? And it should be screaming out at you hopefully what we're going to do now. We're going to use axiom number 1 of group actions, and we'll say that this has to be equal to g inverse composed with g, where this is composition in the group composition table, acting on the element little a, but then of course g inverse composed with g is just going to give us the identity in our group, so we'll then get the identity dot a, and of course we know that the identity dot a is equal to little a no matter what little a is equal to. Okay, and that's how we can prove that sigma g inverse of sigma g of A is equal to little a for all little a in the set capital A. Okay, now the second part of this equation here follows exactly the same logic, and I'll go over it again just to reaffirm the argument in your head. Okay, so we now want to prove that sigma g of sigma g inverse of little a is equal to little a for all little a is an element of the set capital A. So again what we do here is we just use the definitions again. Okay, so firstly we'll start off with sigma g inverse of this element little a, and that is just going to mean g inverse dot little a, so we can rewrite that as G inverse dot little a, G inverse acting on the element little a, just by the definition of the mapping sigma G inverse. Okay, and then what we're going to be doing is taking sigma G of the element of the set A, G inverse dot A, basically. Okay, and this will then be G dot G inverse dot A, again just using the definition of this mapping sigma G. Okay, and again what we can then do is use axiom number 1 of group actions and say that this answer here, G acting on G inverse acting on A, is just going to be the same as compose G with G inverse in the group composition table, act that on the element little a, okay, and then what we can do is we can rewrite G composed with G inverse in the group composition table as the identity element, so we'll get the identity acting on A, and of course the identity acting on A by axiom number 2 of group actions is just equal to A for all little a is an element of the set capital A. Okay, so what we then have done is proven that this mapping sigma G inverse, this mapping from the set A to the set A that is associated with this G inverse element, the inverse element of little g in the group, is actually a two-sided inverse for our mapping that we have associated with the element little g. And that now proves that this mapping that we have associated with the element little g from the set A to itself is in fact a bijective map. So what we have now proven is that we have successfully associated a set permutation of the set A with the element little g from our group. And of course little g was just an arbitrary element of the group, so we've done it now for all elements of the group. So what I have now shown you then is that this does successfully associate with all of the elements of the group capital G a set permutation of the elements of the set capital A, and the way that you do this is quite simply by this rule. Okay, we'll have a break here, and then in the next video what we'll do is we will see why these set permutations that we have associated with each element of the group are actually consistent with the composition table that we have on the group. What I want to make sure is that the composition law that I have on the elements of the group, that is the same as the composition table that I would get if I defined composition of group elements by composition of these set permutations of the set A that I've just associated with them. And we'll see how the axioms of a group action are going to make that all work out perfectly.